Hello, my name is Professor Matthew Schmidt, and I'd like to welcome you to Genetics. In this session, we're going to talk again about linkage and gene mapping, but specifically we're going to speak about the so-called chi-square test, a test that measures goodness of fit, which is a concept we'll explain, well, right now. So the real idea of this is we've seen situations where genes are not linked. We've seen situations where they're clearly linked, but we need some kind of statistical method of determining, based on given data sets, if two loci are in fact linked, because sometimes it's not 100% clear. So, as I say here, sometimes it's obvious, and those are the times that we've been looking at, but sometimes it's not. And you may be given questions asking simply, are these two loci linked based on this data? Well, the chi-square test, and we should get one thing out of the way right away. The Greek letter chi superficially resembles an X, okay? So here's what it looks like if it's drawn out. In fact, you may remember the word chiasma that we used. It actually is the word meant because it looks like an X. So often this chi versus X, but you don't want to call this the X square test. And also I've heard people call it the chi-square test. No good. So it's chi-square, but just to remember that chi looks superficially like an X. So the question we're asking here is, given data, how would one determine if two loci are in fact linked? So the chi-square test is one method of determining, and what it really determines is how closely predictions correlate with results. Because as we're going to see, if you make a hypothesis that two genes are unlinked, you can say, okay, if that's the case, then this is what we should observe. And then you compare that with what you actually do observe, and we put it into this fancy looking formula. It looks a lot fancier than it really is here, though. In the green box, that is the chi-square formula. So chi squared equals, this is the Greek letter sigma. Sigma, you may know, is used to denote the sum. So it's the sum of, and we'll do this, but the observed minus the expected, that number, because it's in parentheses, squared, that's where the squared in the chi-squared comes from, and then you're going to add up all those depending how many classes there are, and divide it by the expected. So some people will make you memorize that chi-square equation, some will provide it for you. It's not that, once you understand the concept, it's not that bad, but it's sigma parentheses observed minus expected and parentheses squared divided by E. When we actually do it, it should make more sense, okay? If it doesn't already. All right, so in other words, here's the situation, and I kept the formula on the top there just so we can refer to it if we haven't memorized it yet. So we've got a cross, and the cross is big A, big B, little b, times little a, little b, little b. This is of the form of that we've done recently. So our hypothesis is going to be a null hypothesis, which basically means we're saying that the genes are unlinked. Nothing's going on. That's the hypothesis. And if they are not linked, if you do this, we've done it so many times before, we really don't need to do it again. If you do a Punnett square, though, if you're not convinced, we should see a 1 to 1 to 1 to 1 ratio if they are not linked. Okay, so in other words, say we counted 500 offspring. We would expect 125 of each type, because remember, if they're unlinked, independent assortment is what's going on. And in theory, we should see mixing and matching. We should see all types. So big A, big B, little a, big B, big A, little b, and little a, little b. And that's our shorthand for phenotype, remember. So in other words, we know in real life you never see the exact numbers, but just to illustrate the point, I'm going to say when the expectations equal exactly the observations, we'll see what's going to happen. And then we'll see what happens when those observations deviate a little bit more from the expectations. All right? So this isn't actual data, but I'm saying it's actual data. It's data I've made up to illustrate this point. So we just said that we expect, out of a total of 500 offspring that we're going to count, exactly 1/4 of each type, 125, right? And if in fact, unlikely as it may be, we observed exactly that, that would mean that our predictions or expectations were exactly correct in the real world. That's what we observed, exactly what we predicted. So if you look at the formula, just plug in the numbers here. So what is chi-squared equal to? And the math down here looks intimidating, but you'll realize that it's very, very simple after we go through it. But I want to go through it because I want you to understand, if you don't already, how these parentheses fit into things up here. Okay? So what I'm saying is there are 4 classes here, right? In other words, we're dealing with 4 pieces of data, if you will. And that means we're going to have 4 numbers in that box. We're going to square each of them, and we're going to take the sum of those 4. So in other words, they're all the same. It's redundant, but we have to do it this way. So for class 1, look what we want to do. Observed minus expected. Well, observed is here, minus expected. It's 125 minus 125. Obviously, that's 0, and 0 squared is 0, right? So we got a big 0 there. Then we are going to divide that by 125. I may have misspoken a little bit earlier. The sigma applies, really we should put another part in here. It applies to the sum of the entire expression for each one of the classes. I apologize about that. But if you follow down the bottom, you'll understand exactly what's going on here. So 0 squared is 0, and 0 divided by 125 is obviously 0. Now, you can go through every single one of these. We're adding them all together, but they're all going to be zeros. And you can see down here that obviously 0 plus 0 plus 0 plus 0 equals 0. Now, this is an idealized situation, but we end up with a chi-square value of 0. So the only way to interpret this type of data is that you have to be provided with a so-called chi-square value table. So let's take a look at that and understand what it means. So here's a table of what they call critical chi-square values. You'll see something like this if it's not exactly like this. Now, it's somewhat arbitrary, but this is what's been agreed on by everyone, I guess. This right here is a very important line. Sorry, mine's not exactly straight. The null hypothesis is the one that we just made, which is that these genes are unlinked. By the way, this can be used, I said, in all sorts of ways, but in genetics, this is mainly the way that it's used. So in other words, they're saying this. If you get a chi-square value that falls on this side of the line, and the line represents, by the way, a 5% probability that this deviation occurs due to random chance. In other words, just for no particular reason. It's basically set, and what's been agreed upon is that if it's less than 5%, then we're going to reject the null hypothesis. Guys, it's possible that this is incorrect, but this is the accepted wisdom, and it's going to be this way if you're asked to solve it. If the chi-square value falls on this side of that line, well, we don't reject the null hypothesis, which is not identical, but pretty much the same as saying that we accept it. We accept that these genes are unlinked, right? Now, in the case we just saw, we postulated that they were unlinked. And what chi-square value did we get? First of all, the degrees of freedom is the number of classes minus 1. We had 4 classes, so we're looking at degrees of freedom, and all the problems in this set, the degrees of freedom will be 3. But that's not always the case, so be careful. It's always the number of data values that you have minus 1. So we're interested only in this area over here. Now, 0, they don't even bother writing because it almost never happens. But up here, in other words, what they're saying is it's 99% or greater chance that the deviation we saw, we didn't actually even see any deviation, but in other words, the no deviation that we saw, it's almost 100% probable that that's just due to chance. So in other words, that's going to say we're not rejecting the hypothesis, we're accepting it, that the genes are unlinked, right? Now, perhaps it's obvious when the data come up exactly with the expectations that that's what's going to occur. And in fact, look at this. What number would we have need to see out of chi-square so that we can start thinking about rejecting the null hypothesis? We need to see something around 7, right? Between 6 and 7. Actually, 0.05, the value is this one here, 7.81. Technically, it would have to be greater than that for us to start thinking about rejecting the hypothesis. So quickly, let's just go through a few of them so you get the idea. All of these are of the same form, so I don't want to rush it, but I don't want to bore you with, if you understand it. So here, the cross is exactly the same, the hypothesis is the same, and we're going to count 500 offspring, right? Again, you'd expect a 1-to-1 to 1-to-1 ratio, or 125 of each. So I made it here so that they're just slightly off. So instead of 125, you saw 130 of one class, you saw 120 of the other class. So we don't have to do it for every single one, but it's observed minus expected, right? So for the first class, that's 130 minus 125, which is 5, right? We're going to square that. 5 squared is obviously 25, and then we're going to divide by the expected, which is 125. And if you do the math for that, you come up with 0.2, all right? Do it for all the classes. Here, this class, again, they're identical, so we know that's going to come up to a 0. This one is over here, 120 minus 125 is obviously negative 5, but negative 5 squared gives you the 5 again, and 5 squared gives you 25, which we'll divide by 125 and get our 0.2 again. And then this last class is going to give us a 0. So now we've come up with a chi-squared value. You see minor deviations, and this is something more like you might see in real life for unlinked genes. And it comes to 0.4. So quickly, let's go back to our chart here. 0.4 is somewhere around this vicinity, right? And that means that the deviations that we saw, there's a chance between 90 and 99% chance that this is just due to random fluctuations, not some phenomenon like linkage. Okay? So I hope you're catching on. We're going to keep going and keep getting further and further away from our expectations. So here is one where it's going to be sort of almost on the border. I hope it's good with you that we don't have to say this every single time because it's the same type of cross, the same expectations, etc. Now, I've made the numbers, obviously in real life it might be a little less, I've made good, solid, even numbers here just to illustrate the point. So instead of 125, we see more 140 of these two classes, and we see 110 of these two classes. That's somewhat of a deviation, but this is why this test had to be invented. You can't just look at it and go, yeah, it seems like enough to me. We have to have some kind of rule or some kind of standard to go up against. So let's do the math here. 140 observed minus 125 expected gives us 15, right? Then we're going to square that, which will equal 225, and 225 divided by 125, you can do the math on your calculator if you want, but you're going to come up with 1.8, all right? And since this second class has the exact same number, we're going to get 1.8 for that as well. It's probably not that shocking. If you do 110 minus 125, you get negative 15. But of course, when you square that, you're back to 225. So the value for all four of these is identical, 1.8. That's where the sum comes in, the sigma, where you have to add up all those values, and you'll come up with 7.2 as your value for chi-squared. Now let's go back and look. I think I'm going to erase most of this stuff. We'll keep this line. Remember, it just so happens that we're using degrees of freedom 3 because of the way this was. It differs greatly, so be very careful about the degrees of freedom. Remember, the number of data classes minus 1. Now, the number we just got was 7.2, and it looks like it's sort of in between here, right? But here's the thing. This is a probability of 10%. This is 5%. So this is really the magic number, if you will, 7.81. The number we got was 7.2. So it really does fall just this side of the line that we've drawn, right? So even though it's close, we're still going to have to say we're not going to reject the null hypothesis, which means we're going to accept it, which means we're right about at the limit of deviation where we can still say, well, these genes are unlinked as far as we can tell. Because, you have to be fairly sure that these deviations are not just random chance. Random chance can cause quite a bit of deviation. So only when we get a number higher than 7.81 are we going to say, you know what, this is too much in a way. Too much deviation. And we're going to reject that null hypothesis. Remember, the null hypothesis is that the genes are unlinked. If you reject that, it's basically the same thing as saying that they're linked. We can't prove they're linked, that's why it's worded this way, but that's probably for another topic. So let's see a situation where I didn't make the deviation ridiculously more, but I made it, instead of seeing 125 of each, I saw 150 of two classes and 100 of other classes. Now, look, I know in real life they may have numbers like 143, 129, it's fine because you're always doing the exact same thing. The math might be a little bit more of a pain in the neck. Just be careful. It's addition and subtraction. So 150 minus 125 is 25, right? 25 squared is 625. And if we divide that by 125, we get a round number of 5. And I hope you can see, for the reason it always was before, all the other values are going to be 5 as well. I did this, like I said, I don't want to rush it, but I don't want to laboriously go through this when I think you can understand it this way. Then you can laboriously go through it when you're given a problem, and you can check out in the problem solving section to see if there's one that's more akin to what you might see in reality. But here we've got 5 plus 5 plus 5 plus 5 giving us a whopping chi-square value of 20. So check it out. I mean, and this is why I did it this way. If you just compare this with what we had before, 140 and 110, right? And now we've got 150 and 100. It doesn't seem that ridiculously different, right? Well, we got a chi-square value of 20 now. Let's go back and look at our chart. Oh my goodness, 20 is over here. That means, look, before we were saying, well, we've got a greater than 5% chance, between 5 and 10%. Now we're below 1%. We're below 1/10 of 1%. So the way the chi-square formula works, seemingly small deviations can lead to a large chi-square discrepancy here. And that's why this is one of those things you can't just say, I don't know, it looks like they're linked to me. This is the agreed upon standard. So the technical way to say this correctly would be, since we got 20, which is not even on the chart, we know it's all the way over here, that the deviation we just observed, there's less than a 1/10 of 1% chance that that deviation occurs due to random fluctuations or random chance. That means we're going to reject that null hypothesis, which basically means we're going to accept the alternate hypothesis that these are linked genes. Okay? So some people think the chi-square test is a little bit of a pain in the neck. I want to just do one thing, because even though, well, let me just do this to make sure it's clear. The way I originally wrote it, and I think the way I originally said it, we want to really be clear that what we're adding is this entire expression that I put in the red brackets here, okay? So I'm sorry if that wasn't initially clear, but you'll get one of that whole expression for each data point. It's not really a point, but for each comparison of an exception and expected to an observed. And then when you do the squaring and the dividing, you'll get a value, and you'll sum all of those values. We always had 4 in these questions, but it depends what kind of a cross you're doing to see what you'll have. So be careful of the degrees of freedom. It's not so bad to memorize this formula, especially if you understand what it means. And no one expects you to memorize this, I don't think, to memorize this type of a chart. I can't imagine that that would happen. So you should be provided this chart or something like it, probably without all the scribbling on it. So check out a problem, perhaps or two about that, and think about it a little, and I'll see you soon.